So he did this RMT domains. Proper ideal. And you the unit conceived. Then I survives. He did that, didn't he? Okay, good. That was going to be kind of useful for us. And he said did he do? Did he prove for you that if there's a domain, so I'll prove this for you as here, this is a really righteous theorem. Let R be a domain. With quotient field. K, and I and R are proper ideal. Then there's a valuation overring such that I survives. Valuation overring. And R such that I survives. Did he prove this for you?
He gave us like a very sketchy, quick explanation, but didn't really go in depth at all.
Do you want me to go into help? Okay, let's this is important, and we're going to use this for a nice application later. And basically, what it says is, okay, take your favorite interval domain, and it's got some proper ideal in it. Then you can find valuation opening for R where I still survives. That is, it doesn't blow up the whole thing. So, for example, valuation opening. To talk about examples. I'm gonna start beating up on some examples. You might know a valuation ring for that survives. Of course, the integers itself is a valuation ring. The quotient field is a valuation ring, but 2z wouldn't survive the quotient field, would it? Right? Because now you got 1/2. I think this probably shows that this is a theorem of proving, right? Because does anybody know? Z localized. Let me kind of go over this a little bit. Remember how localizations work? these are the prime ideals and the integers, right? 0, of course, and then 3, 5, all the odd primes. Right? When you localize this, remember what you're doing is you're turning everything outside of this ideal into a unit. Right? So all this stuff becomes units. And basically, what you get is you get this new see localized 2. Remember, in a localization, there's a one-to-one correspondence between prime ideals of the original ring that missed the set and prime ideals of the localization. So now there's only one prime ideal. And that's essentially why it survives, right? In fact, take a typical element here. Any element in C localized 2 can be written in fraction form. Here's what I'm going to do. I'm going to jerk all the powers of 2 out of A that I can, leaving this with sort of a naked numerator. That is, you've got no more powers of 2 in there, right? But, and notice that this element is a unit. It can only be n is equal to 0. Right? Because if n equals 0, neither A nor B has a factor 2 in it, so you can convert it. And of course, the more factors of 2 that you have, the sort of deeper you are in that prime ideal. Right? How many of you have ever heard of p-addicts? This is you can use this. You can use this in here to sort of measure how deep in the prime ideal is. You can use this like a metric. Like it's a metric space, but it's very non-intuitive, right? In this metric space, which you use using the powers of 2 to measure how close you are, any interior point of the circle is the center. And all triangles are isosceles. Right? It's very strange. Maybe we get time on it if I can show that. But anyway, the upshot is notice that 2z survives in this, right? Because if you look at two is not a unit in here, so this ideal survives, right? But this actually shows you that this is a worthwhile theorem because it wasn't clear, was it, that you had such. So how can we do this? Well, this is actually Zorn's lemma. And consider. So I'm going to Zornify this by considering a particular set, and I'm going to look at all pairs. Let's say R, let's say, where RJ is an open. And let me remind you what I mean by an open ring. I mean, it's a subring fraction field. So it's a ring that's contained between R and its quotient field K. And IJ and RJ is a proper and since the die is contained in IJ. And I'm going to partially order this as one would do in Zorn's lemma by the following relation. I'm going to say that I'm going to partially order this by saying R alpha, I alpha, plus that are equal to R beta, I beta. It's known if R alpha 10 beta and I alpha. So, in other words, you only, and remember, this is a partial order, then a total order. So, for example, even if these two are the same ring, these may not be, these aren't comparable unless this one is contained in this one. So you have to have both these conditions going on. We want to get an upper bound. So we want to apply Zorn's limits. We need an upper bound for this chain or a chain. To apply Zorn, we consider the chain. Let's call it C. So this is a chain. So if I take any two elements, any two ordered pairs of this chain, one of them plus that equal the other. And of course, as you may guess, we're going to show that TJ union. Well, I'm going to call it. And here's what I mean by union. Chain, that is T is equal to union RJ. And A is the union equals. Now, let me at least discuss the details here. Everybody okay where we are? So, okay. Let me point out T is a ring. In fact, it's a ring. In fact, it's an over-ring bar. Because every one of these things is an over-ring bar. And so the quotient field of T is contained in quotient field of the ring bar. And A and B is and it's proper. Right? We've seen that unions of ideals, be careful about that. We say that unions of chains of ideals are an ideal, right? And why is it that A is proper? Right, right. So all the I's were proper. That means none of the I's contain one. So their union can't contain one. So A can't contain one. So it's proper. So is everybody warm and snugly with it? Okay, T is an over-ring of R and A is not. Okay. So no, it's a proper. A is a proper ideal of T.
Right. But it wouldn't be sufficient, right, to say that it's just like one, like obviously this just to say it doesn't have one. But T could also not have one.
No, T has to have one because all the rings along the way have one. Right, because this is, T is a union of a bunch of domains, and even the smallest one has one, right? And actually, there's a sole point here, because depending on whose definition you want to argue about what needs to be a subring, we're assuming that the identity of all the subrings is the identity of the victim. So TA is an upper bound of course, yeah, it's a pair, person over A, yes, and of course the ideal A can be five. So now we can apply some. We have maximum element. Is an ovary. R, J, and B. Proper ideal. And I. Okay. So notice, when we first notice that no. IB is contained in J. So I survives. Okay, so here's what we've got. We've got that this maximal element satisfies the fact that I survives. Okay, well, that's no big shocker. Big thing is to show this is valuation. Okay. To this end, so such that neither alpha nor alpha inverse. So in other words, what we're doing is we're assuming this is not a valuation of well, notice that notice this IB's proper identity. IB survives in either on alpha or So there's this larger domain. Here's this domain, or D. And this would be our desired computation. Those ones limit, let's pick out maximum elements of cell. Okay, here is. Just have this as an exercise. Actually, so maybe before we look at this kind of, let me give you the theorem. I'll come back to prove it. This is kind of a big theorem about valuation domains, and then I'm like, before we go and prove this and do something that's up a little bit, miss. Let R be a single domain. R bar is the closure of R. Remember what that means is that's everything in the quotient field is integral. Then R bar is the intersection R bar is the intersection of all valuation elements. This is a big theory. This is big theory wise, and actually there are some instances where this is a nice application too. But the integral closure of any ring is the intersection of all valuation elements, which is super cool. Okay. There are many non-isomorphic theory and evaluation domains. However, from one point of view, they all look the same. These are all local PIDs. So let me prove to you that any local PID is a. By the way, it should be clear, I think, that local PIDs from the theory Because PICs, their ideals are not only finally generated, but principal, right? And once you localize, it's still principal. So, of course, fields come under this category, right? Fields are local PIDs in a very boring way. It's the only prime is 0. So, maximal ideal generated by I. This is standard. I don't need 3.4. This is my notation. And this is prime. So any element R is a form. Yes, non-zero is important here. U I K. Where U is in units are and I, but I K is in natural number. U is not unique because it can vary by unit, or well, it may not be unique. And it's commonly called a uniformizer. But notice, think of it. So here's a quick proof of this. Okay, so we're forgetting about 0, right? Here are the units, and it's not unit, it's a PID, so everything's a product of primes, right? Like it's UFD. Well, there's only one prime, so everything is just a power of that prime. And I can tell you why it's valuation domain. If you have two elements, U1 pi K1 and U2 pi K2, whichever one has the smallest exponent of pi divides the other. So it's valuation. Okay. This is why I see localized to work, because these are PID and now localized in it. In fact, here's some real life examples. These are all the theory and valuation domains. Here's another one. Here, the uniformizer I is equal to prime P. Let F be a field. Power series. The theory and valuation domain. And here, the uniformizer I is equal to X. Because in the power series ring, every element f of x is x to the k, g of x, where g of 0 is not 0. And remember, in power series ring or field, if your constant term is not 0, you're a unit, right? Which is exactly what we have in this form. And there are others that look like, and notice these all have kind of the same theme to them, right? Because every element in there, it's not 0, it's a unit times a power of whatever that unique prime is, right? Here it's P, here it's X, but you can do other things. Let f of x in the polynomial ring be irreducible. Again, that's a field here. So it's prime. Notice f of x is a PID, like it should be. F that's localized at that prime. Because again, this is a PID that has only one non-zero. And of course, I didn't talk about it, I just mentioned it probably earlier, but all fields are examples of Noetherian valuation. Notice that notice that on the theory and valuation domains are small in quality sense. They're either fields, in which case the maximum ideal is 0, or they're not fields, in which case the maximal ideal is the only non-zero prime. Right? So for example, the only primes in Z localized to P, the ideal generated by 0 is 0, the ideal generated by P. So it's just a stack. Here, in fact, here's what the prime ideals look like in the theory of evaluation. Only 0. Or so the theory of evaluation domains are either dimension 0 or very small. Valuation domains exist of every dimension, but if they're any bigger than that, they can't possibly be theory. By the way, even if they are one-dimensional, by the way, any valuation domain of dimension 0 is automatically a field. In fact, you don't have to use any fancy terminology in here. Any domain of dimension 0 is a field. Right? Now, valuation domains can be of dimension 1, that is, only have one non-prime ideal that's not 0, still not being theory. Anybody know how to build one? Can anybody build a valuation domain that looks like, if you have this prime ideals, it looks like this: 0 ideal and then maximal, and there's no other primes. That's not there. So in particular, the maximal ideal can't be found. This is my favorite part. It's really weird examples. But this may look a little weird, but these are actually very important in structural ring theory. And in fact, I'm going to build you some bigger valuation domains that are actually important in number theory. This one's important as well. So let me give you one here. And this will require a little bit of faith, because this will require some stuff that I can't give you yet, but in this quotient field, is an algebraic closure Q. So it turns out that every element of this quotient field is algebraic over Q. In fact, and it's algebraic closed. So this is basically everything that we ever thought about. We got a lot there, guys, from we got right, every possible we've ever probably know, right? Money, right? Now, this by itself is not a valuation domain, because it's not even crossing over. However, this is the part that, and this ring is very important. Remember there. Notice that 2 I think we can all agree that 2 is a prime integer, but it's not prime in this ring. Anybody see why? It's not even introduced. For example, or I can do this all day, right? 2 is wildly not prime. In fact, this ring is so defective, it has no irreducibles whatsoever. Because whatever you have in there also has a square root. But P, the prime ideal, C, oh, actually, let me do this part. Let me do that. Let me make that observation. It's not a unit. Can you explain why? It works. Yeah. But 1/2 is not infinite. Because for membership in this club here, 1/2 would have to be a root of a monic polynomial with coefficients of z. We've already proved that 1/2 is in fact not integral over z, so there's no 1/2 there. So 2 is not even. Everybody okay? The prime ideal such that since 2 is not a unit, I know such a prime ideal exists. And in fact, in this ring, it's maximal. In fact, just like the ordinary integer, because this is integral over z, and this is something we'll get into more in commutative algebra. But since z bar is integral over z, the dimension is the same. So in other words, all non-zero prime ideals are maximal. Let's be honest here. If you look at C bar, localized P is a one-dimensional. So it looks like this. Non-theory. this example is probably not that fully, because I just told you where to find it, how to construct it. By the way, does it matter what prime you pick? No. And in fact, there are infinitely many primes that is contained in this ring in any one of them part. And in fact, there's nothing special about two. But if you take any of the maximal ideals in this ring and localize it, you'll get one dimensional number. Let me get my hands dirty, and I'll actually build you one in the spirit of this, so you can see. I'm going to start with the field Z2. Actually, my Z2 doesn't matter so much. I just want that to be a field, but the Z2 will make my computations a little bit easier because I am a lazy man. What do I mean by that semicolon here? This is a group. So what I mean by this is these are polynomials, so to speak, with variable x. But now I'm allowing my exponents to be taken from Q, the positive or non-zero ones. This is sometimes called a monoid domain. That's the monoid. So a typical element here looks like epsilon 0 plus epsilon 1 x to the a1 plus epsilon 2 x to the a2 epsilon k x where epsilon I is in T2 and the exponents ai are in Q. So it's basically like polynomials, except I'm granting a little bit more latitude, if you will, with the exponents. Right? So I've got all kinds of stuff in here, like 1 plus x to the 3/7 plus x squared plus x to the 96 over 37. Crazy crap. And my coefficients are only 0 and 1, so that make my life a little easier that way. But again, this can be. Now, in this case, what I'm going to do, this brings a mess. I'm going to let M be the ideal generated by x to the alpha. So basically, this is the set of stuff that F has 0 constant. And now I am going to pass to the new ring, but R, my original ring, localized to 0. Okay, I know this may sound a little bit confusing, but let's try to straighten this out a little bit. So first of all, my ring has these kind of liberal polynomials, right, that are allowing rational exponents. Now what I'm doing is I'm allowing all the polynomials that have constant term 1 to be a denominator. Right? Now, I'm going to try to convince you all that this is in fact valuation. Let me first point out considering this notice, you might protest and say, well, a typical element of this thing looks more general than this, because it's actually something like this divided by the polynomial, right? Because remember, the localization allows my denominators to be outside that maximal ideal. But even if I have that denominator, I'm just going to clear the denominator and just consider the numerator, because it varies only by a unit, right? Now notice that if epsilon 0 is 1, then this is a unit. Because it's not an M, right? It's not an M, so it's a unit. Right? And what if not? We assume alpha 1 plus alpha 2. So I want to always put my exponents in increasing order, and I am going to assume that none of these epsilon i's are 0. They're all 1, because otherwise, if this is going to be 0, why would I start here, right? So if I have two elements here, notice that this one right here, we have x to the a1 plus x to the a2. A1 plus A2 plus, and pull this x to the A1 out. A1 plus x to the A2 minus A1. And because of the fact that these are increasing in size, all these exponents are positive. Don't have to worry about violating that. Great. And this is a unit. So, conclusion. Any non-zero element, whatever I call this, R, is formed x to the A, and U. A is greater than 0, and U is a unit in R. Because it's either a unit to start out with, and notice that the unit's already at this form, you can just take A to be 0, or it leads with something, it leads with an exponent like this. You can pull that out, and it's that times a unit. So this is valuation, because take any two non-zero elements and compare them. The x to the A, U, x to the B, B, or A, B, and well, A, B will say greater than or equal to 0, and Q, U, B, units R. One of these divides the other. If A plus center B, x to the A, U, B. B is less than or equal to A, the reverse is true. Any questions on that? Notice that the maximal ideal of this valuation ring, it cannot be finitely generated. Because if it's generated by only finitely many elements, you can assume they're of the form x to some power. There must be a smallest one if you only have finitely many, right? So if it's generated by x to the A1, x to the A2, x to the AN, we can assume that x to the AN is the smallest one. How are you ever going to get x to the AN over 2, right? So it can't possibly be finitely generated. Any questions on that? I'm gonna do some examples next time before I prove the theorem. But ask yourself this, now we have built zero dimensional valuation domain for fields. We've built ones that are PIDs with only one prime. Now we've built one that's only got one maximal ideal. It's not, it's only got one non-zero prime ideal, and it is not an Ethereum. How can you build them taller? You might think I can build with stacks of primes that are high. We'll talk about that. Questions? Okay, well, I will catch you all on the flip side.